And with that, good morning everybody. Welcome back to linear algebra. We'll look at the board for a second to remember what class it is. Plan for today is we are going to continue our discussion of eigenstuff from last week. Today focusing on how do you find all the eigenvalues and eigenvectors of the matrix algebraically as opposed to kind of the more geometric approach we focused on in the last class. So my office hours. My office hours are all mixed up for the next 2 days for a variety of reasons. So I think I told you all last week I was expecting to maybe have office hours this morning, but not this afternoon today. Turns out it's the opposite. I have to cancel my morning office hours at 11, and instead my only office hour today will be from 1 to 2. And tomorrow, instead of my usual 1 o'clock Tuesday office hour, I'm just going to have an office hour from 10 to 11:30 instead. So, my normal Tuesday morning appointments are canceled. But I have a Tuesday afternoon appointment instead. So here's the deal. If you want to retest this week, you're welcome to send me an email and come by either of these times. If you can't make either of these times, send me an email anyways and maybe work something out. As far as homework goes, have a good break. Enjoy yourselves. Linear algebra will wait until we come back. John?
Other classes won't wait.
Well, you know, I don't care about your other classes, so your other classes is a you problem, not a me problem. Okay, so if you can't tell by my voice sounding a little bit off today, I got sick over the weekend. And while I'm feeling a lot better today, that does mean I did not get any grading done this weekend. So sorry about that. I'll catch up on grading, get back all quizzes, etc. After Thanksgiving break. I'm hopefully by tomorrow I'll be caught up on grading and can post mastery totals for you. Any other questions or comments before we get started for today? What? No, not what. Why? Why was doing algebra always so easy for the Romans? Because whenever the Romans needed to solve for x, they always got x equals 10. Second consecutive class day of Roman numerals jokes.
I never did these jokes.
Okay, did anybody need a copy of the packet for Standard 16?
What?
11?
Standard 16, that's right. I don't know why I said Standard 16.
I thought you said 60, so.
Standard 16.
I just like it if no one else needs it.
Standard 11 packets. Here you go. Yeah, sorry, this is going over my head. Standard 16 again. You'll be fine.
You'll get it.
The eigen packet. Alrighty, let's get going. So last time we talked about what it means to take eigenvalues and eigenvectors for a matrix. We basically said if you have an n by n matrix, an eigenvector for that matrix is just a vector v where multiplication by a will give you a scalar multiple of that v. And if that happens, then that corresponding scalar, lambda, is called an eigenvalue of the matrix. So last time we looked at kind of a few of our standard form matrices, some of the geometric transformations, like a scaling matrix, a reflection matrix, a rotation matrix, and we were able to kind of geometrically reason our way through to finding what are the eigenvalues and eigenvectors of that matrix.
Could I have standard 11?
I suppose so.
Thank you very much.
We talked last time about like when you're doing a rotation or a reflection, etc., what vectors will be mapped to scalar multiples of themselves, and use that to find eigenvectors and eigenvalues. We said if you try and find eigenvalues and eigenvectors used algebraically using the definition, you get some pretty messy systems of equations that you need to solve. So what we're going to be doing today is talking about a different algebraic approach using the theorem that we proved at the end of class on Friday, namely that if you have an n by n matrix A, lambda is an eigenvalue of A if and only if the determinant of A minus lambda times the identity matrix is 0. So this equation right here is often called the characteristic equation. Of the matrix A, just the equation determinant of A minus lambda times the identity matrix is 0. It's a characteristic equation. Characteristic means just, well, it has some messy representation theory things, but for now, what I want you to think of is it allows you to determine the character of the matrix, the morality, the good or the evil of the matrix by determining what the eigenvalues of that matrix are. And then the characteristic polynomial of A is the same thing, just without A equals 0. And it's just the expression determinant of A minus lambda times the identity matrix. So in essence, what you want to do in order to find eigenvalues of your matrix algebraically, as opposed to the geometric approach we took, is you take the characteristic polynomial, you set it equal to 0, you solve for lambda. So let's do some examples of putting that into practice. So start with, I'm going to look at the matrix 1, 2, 4, 3. And I want to find the eigenvalues of this matrix. So, Ashley, is this an obvious reflection or rotation matrix? Doesn't look like it. Reflection just has to be 1, 0, 0, 1 with some negatives mixed in. A rotation matrix, you need cosines and sines of various things, and there isn't a theta alive that if you plug in for, there isn't a real number theta that exists that if you were to take, say, sine or cosine of that value, you would get 4. Or 3, or 2 for that matter. So this isn't a reflection matrix, it's not a rotation matrix, it's just some 2 by 2 matrix. But I claim we can still find the eigenvalues and later on eigenvectors corresponding to that matrix. So if we were to take the determinant of C minus lambda times the identity matrix, well, we're going to take 1, 2, 4, 3 minus what would lambda times the identity matrix look like? Yeah.
Lambda 0, 0, lambda.
Yeah, it's going to be lambda times the matrix 1, 0, 0, 1, which if you multiply that through by lambda, taking the scalar multiple, will give you lambda 0, 0, lambda. And then, true or false? Can we take determinant of the first matrix minus determinant of the second matrix?
False.
Correct. We can't, yeah. The matrix or determinant behaves nicely with respect to products, as we kind of talked about in the last standard, but it doesn't with respect to sums and differences. You can't, the determinant of a sum is not the sum of the individual determinants, which is okay here. That just means we need to combine these two matrices first before we take the determinant. So, Abby, what would we get if we subtracted these two matrices? What matrix would we end up with?
1 minus lambda, 2, 4 minus lambda.
3 minus lambda. So in essence, what we get is we get the original matrix, except we're subtracting lambda from each of the diagonal entries of that matrix. All right, Cameron, how do we take the determinant of this 2 by 2 matrix then?
1 minus lambda times 2 minus lambda minus 8.
Yeah, 1 minus lambda times 3 minus lambda minus 8. Just do the old for a 2 by 2 matrix. If we multiply this out, that'll give us lambda squared minus 3 lambda minus lambda is minus 4 lambda. Plus 3 minus 8 is minus 5. And that right there is going to be the characteristic polynomial of the matrix C. The polynomial in terms of lambda, where think of this as just being like something with x's, but we're replacing all the x's with lambdas. That polynomial is the characteristic polynomial of the original matrix. The polynomial we get from taking the determinant of A minus lambda times identity matrix in terms of lambda. Kevin, so what do we have to do with this polynomial if we want to find the eigenvalues of the original matrix?
So you said equals 0.
Yeah, we need to set it equal to 0 and
Use the that one equation that everyone has the sum to. The quadratic.
using the quadratic formula? Okay, yeah, so in other words, we need to set this equal to 0 and solve for lambda, right?
Yeah.
Yeah, so if we do that, our characteristic equation will be lambda squared minus 4 lambda minus 5 equals 0. And this equation right here is the characteristic equation, the Char-equation. Eleanor, sounds like you don't want to use the quadratic formula to solve this. What would you rather do? Graph it, and see where it crosses the x-axis. That's what Liam wants to do.
That's what I like.
You do that.
Alright, how do you want to do it?
Factor it. Y'all haven't had as many equations like this as my Calc 1 students have this semester. They've had a lot of take the derivative, set it equal to 0, solve for x by factoring recently. All right, Eleanor, how does this factor?
Negative 5 plus
Negative 5 plus lambda.
lambda.
Lambda minus
Lambda
5.
minus 5 and
Please.
lambda plus 1.
Lambda plus 1 is equal to 0. Let's see. Lambda squared minus 5 lambda plus lambda is minus 4 lambda. Minus 5 times plus 1 is minus 5. And Ben, what would lambda have to be then if lambda minus 5 times lambda plus 1 is 0?
5 or negative 1.
5 or negative 1. Yeah, so we get lambda equals 5 and lambda equals negative 1 are the eigenvalues of the matrix C. So in order to find the eigenvalues of your matrix, algebraically, you just find the characteristic polynomial, set it equal to 0, solve for lambda. And yes, Kevin, if we wanted to, we could have said lambda equals negative b plus or minus the square root of b squared minus 4ac all over 2a, which is 4 plus or minus the square root of 20 plus 16 is 36 over 2, which is 4 plus or minus 6 over 2, which is 4 plus 6 over 2, and 4 minus 6 over 2, which is 10 over 2 is 5, negative 2 over 2 is negative 1. We would have gotten the same answer if you used the quadratic formula. If you graph this correctly, then you'll get a parabola that intersects the x-axis at negative 1 and 5.
Now, how do you find the eigenvectors for this?
Ooh, that's a different question entirely. One we'll come back to.
Okay.
But basically, it's going to be, once you know what your eigenvalues are, what we're going to be doing is we're going to be plugging in those values for lambda here and seeing, a times minus 5 times the identity matrix, what vectors can we multiply by that to get the 0 vector is what we'll be doing. But we're going to hold off on that for a few more minutes.
Alright.
Any other questions or comments though about finding the eigenvalues of a matrix? Let's do a fun one. Let's do, in that case, let's find the eigenvalues of the matrix D equals 1, 1, 1, 1, 1, 1, 1, 1, 1. So we're going to need to take the determinant of D minus lambda times the identity matrix. What is D minus lambda times the identity matrix going to look like here? Yeah, Henry?
1 minus lambda, 1, 1. 1, 1 minus lambda, 1. 1, 1, 1 minus lambda.
Like that?
Yes.
Like it. Yeah. So whenever you take D minus lambda times identity matrix, just like here, the only thing that changes from your original matrix is you subtract lambda from all the diagonal entries of your matrix. Oh boy, we need to evaluate this 3 by 3 determinant. Riley, we have a 3 by 3 determinant. Do you have a row or column you would prefer to expand along?
The bottom one.
The bottom row? Why that one?
Because it has the most ones.
It has the most what?
The most ones.
This is not wrong. Technically, every row and every column has an equal number of ones. So this one, I don't think, unfortunately, there's a nice shortcut. Oh, a row with a column with a bunch of zeros in it to expand along. So you could say, oh, the bottom row because it has the most zeros out of all the rows and columns. Well, technically. Okay, we can do bottom row. That'll give us, let's see, 1 times the determinant of 1, 1, 1 minus lambda 1 for expanding along this row. What's going to come next?
Be minus 1 minus lambda. Minus 1 minus lambda. 1, 1, 1.
I'm not giving myself enough space to work, but yes, that'll be minus 1 times the determinant of, you remove the bottom row, second column, so 1 minus lambda, 1, 1, 1. And then, Catherine, how about our last term?
1 times 1 minus lambda, 1 minus lambda.
Like that?
Oh, sorry. I was doing another row. Okay.
If you do a different row, you come out to the same 3 terms, just in a different order. So, I think I disagree with your scalar multiple out in front.
Oh, 1 minus lambda.
Yeah, it's going to be 1 minus lambda, the last entry in this third row, times determinant of what's left if you remove last row and column. Alrighty, good golly. So, if we do our first determinant, we'll get 1 minus lambda minus the quantity 1 minus lambda minus 1 plus 1 minus lambda times, oh boy, 1 minus lambda quantity squared minus 1. How's that for a pile of 1s and lambdas? All right, Eleanor, what's this first term going to simplify to?
What, like just, oh,
What's that going to simplify to?
oh, that's just, lambda.
The 1 minus 1, the 1s will cancel out, and we get a minus minus lambda, so that'll be lambda. Paul Joshua, how about the second term?
Let's see. Just on its own?
Yeah.
Just negative lambda?
Yeah. So The stuff in parentheses comes out to negative lambda, but since we're subtracting that off, we end up adding lambda as kind of the net result. All right, Liam, what's 1 minus lambda times 1 minus lambda squared minus 1? I'd be very impressed if you had that in your head.
Minus 1. It is lambda squared minus 2 lambda.
Plus 1 minus 1. Okay, and then we need to multiply that by 1 minus lambda.
So that negative lambda cubed. Plus 3 lambda.
Plus 3 lambda?
Yeah. And
I'm getting a plus 2 lambda squared from the outside two terms, and then a plus lambda squared. So I think we get a plus. I think we get a plus of 3 lambda squared.
plus 3 lambda squared. And then minus 2 lambda.
Yeah, minus 2 lambda. Oh hey, swoosh swoosh. Question, Cameron?
Oh, I don't. Those aren't. Okay, those aren't fractions. That's just like one that's like the one equation that's like split.
Oh yeah. Sorry. No, these are I just underlining certain terms to say like,
Okay.
hey Eleanor, what is this thing I just underlined come out to? No,
Okay.
those are not fractions.
Okay, cool. Thanks.
So end up with negative lambda cubed plus 3 lambda squared for our characteristic polynomial. Kevin, oh dear, we have a degree 3 polynomial. We can't quadratic formula that.
Oh dear.
So if we want to set this equal to 0 and solve for lambda, how could we solve that equation for lambda?
You could factor out the lambda squared and just be left with, or you could factor out negative lambda squared and just be left with lambda minus 3.
That'd give us negative lambda cubed plus 3 lambda squared. Yep. Okay, so we get negative lambda squared times the quantity lambda minus 3. And if we wanted to solve that for lambda, Noel, what would we get?
Lambda equals 0 or 3.
Yeah. So it turns out we get 2 eigenvalues, just like our previous problem. Questions, comments, concerns?
I don't know why, but like, for some reason I just cannot see how the first term goes to positive lambda.
This term?
Yeah, I'm just.
So keep in mind you have to distribute the minus side.
Okay.
So if you do that, it comes out to 1 minus negative lambda,
Okay, thank you.
which these will cancel out, and negative lambda comes out to.
Okay.
Does that help?
Yeah, it was just not working in my head.
And it is a little bit of a. Whenever you have the same term showing up a whole lot of times, like 1s and lambdas in this case, it can make for a bit of a mind bender, I think.
Yeah, definitely.
Yeah,
Is
and
it always gonna be 2 e-values regardless of the matrix?
it's always going to be what?
2 like e-values, like regardless of how what matrix it is? Like if it's 2 by 2, 3 by 3, 4 by 4, will it always just be 2?
Well, let me ask you this one. I'm going to give you a 1 by 1 matrix. How many eigenvalues does this matrix have?
1.
All right, if we take this matrix minus lambda times the 1 by 1 identity matrix, and take the determinant of that, well, that's the determinant of the 1 by 1 matrix, 5 minus lambda, which is 5 minus lambda. How many roots does that polynomial have, Abby? Which is?
Lambda equals 5.
Lambda equals 5.
Okay.
So the answer is no. It's not always going to be 2 eigenvalues. It's a good hypothesis. It's supported by the original 2 examples we did. I will tell you this. hit, the maximum number of eigenvalues that you can have is going to be equal to the number of rows and columns in your matrix. So a 2 by 2 matrix is going to have 2 eigenvalues at most. A 3 by 3 matrix will have 3 eigenvalues at most. Why does this one only have 2 eigenvalues though? It came from a 3 by 3 matrix. Oh,
Isn't it well, because lambda squared, so it shows up twice.
yeah.
So they're technically 2 0.
You could technically think of this as being 0 is showing up as a double eigenvalue, and 3 is showing up as a single eigenvalue, if you want. And that, the fact that 0 sort of appears twice as a root of the characteristic polynomial is going to have some fun eigenvector implications.
What if they had like a 2 by 3 matrix?
Generally, when you're doing eigenvalues and eigenvectors, you only want to look at square matrices, n by n. Mainly because if I gave you a 2 by 3 matrix, that's not something we can take the determinant of. Also, if we had a 2 by 3 matrix, so let's say 1, 2, 3, 4, 5, 6, what would be the inputs to the function of multiplication by that matrix? How many components would our input vectors have? If you're going to take rows of this matrix dotted with columns of this matrix, in order for the dimensions to match up, how many entries would you need? Okay.
3.
Yeah, we would need something like 3 entries, like an x, a y, and a z. Because if we're doing the matrix multiplication, we would need to take like 1 times x plus 2 times y plus 3 times z in order to make the dot products work out. How many entries would the output vectors have? Eleanor?
2.
Yeah, it's going to have 2. We'll have something like x plus 2y plus 3z, and 4x plus 5y plus 6z. So Kevin, let me ask you this. This is going to be a vector in R2. This is going to be a vector in R3. Is it ever possible for a vector in R2 to be a scalar multiple of a vector in R3? That doesn't sound right to me either. Yeah, you take a scalar multiple of an R3 vector, you should get something in R3, right? So basically, if A is not a square matrix, this equation will never happen. You can't possibly, if A is, say, a 2 by 3 matrix, then A times any vector V will never be a scalar multiple of V, so it wouldn't have eigenvalues or eigenvectors to look for. So, in other words, if you don't have a square matrix, an n by n matrix, same number of rows and columns, then it doesn't really make sense to look for eigenvalues and eigenvectors in the first place. Good question, though. Any other questions or comments related to what we did here? Okay, so now that we've kind of talked about how to find eigenvalues, kind of algebraically, maybe I'm going to come back to the question you asked earlier. What happens if we try and look for eigenvectors? And that is going to lead us into yet another eigendefinition, the eigenspace associated to an eigenvalue. So what we're going to say is if lambda is an eigenvalue of matrix A, the eigenspace of A associated to lambda is going to be the set, which I'll call E sub lambda is going to be the kernel of A minus lambda times the identity matrix. Which, if you kind of parse out what does that mean, well, that's just precisely the set of all vectors V in Rn such that A minus lambda times the identity matrix V is equal to, or don't close that yet, is equal to 0. Which in turn is going to be equal to the set of vectors in Rn, satisfying that A times V is equal to lambda times V. So what does this set of vectors look like? The set of all V such that AV is equal to lambda V. What kind of vectors V are we talking about? Ellen? Yeah, it's basically, when we talk about the eigenspace, we're talking about the set of all eigenvectors associated to it. Plus one more vector. Because unlike, there is one vector in Rn that will satisfy this equation, yet not be an eigenvector. What's that vector is that?
The 0 vector.
Yeah, so technically this is the eigenvectors that get associated with lambda as well as the 0 vector. So we can say, in general, E sub lambda consists of the eigenvectors of A associated with lambda associated with lambda meaning vectors V such that AV equals that specific lambda times V, as well as the 0 vector. So here's a question. The eigenspace associated with lambda is defined to be the kernel of a matrix. What do we know about the kernel of a matrix vis-a-vis its relationship with Rn? Specifically, what type of subset of Rn is the kernel of a matrix always going to be? That we proved back in Standard 5. William?
It's the number of irregularities there. That it's gonna be it's gonna be n minus the rank.
Will give us the dimension of it. But what are the sorts of things that we could even find dimensions of in Rn? Not subsets of Rn, but subspaces. Yeah, so it's always going to turn out that E lambda, since it's defined to be the kernel of some matrix, is always going to be a subspace of Rn. Which means the set of all eigenvectors corresponding to a single lambda, if we tossed in the 0 vector in addition to those eigenvectors, is going to give us a subspace of Rn. And what are the sort of things we can do with subspaces? Well, we can find their dimension. We can find, with some rank nullity chicanery. We can, but we can also find spanning sets. So when we talk about finding eigenvectors of a matrix, usually what we're going to do is find a spanning set or a basis for the corresponding eigenspace of that matrix. So let's put that into practice. Any questions or comments before we move on the page?
No, it doesn't work. So
What does
in
work?
the matrix D, when it was 1, 1, 1, 1, 1, 1, 1, 1, 1,
Mm-hmm.
so you could have an eigenvector be 1, 1, 1, and then the lambda would be 3. If you multiply by that, and you could also have 1 be 1, negative 1.
Hold on, I need to write this down.
Alright.
Okay, so this was our D. We got lambda equals 0 and 3 as our two eigenvalues.
And then, so you could find an eigenvector that goes 1, negative 1, 0.
1, negative 1, 0.
And that one corresponds to 0.
Because if you took 1, negative 1, 0 does correspond to 0. I agree.
And then you could have one
We're going to prove this here in a few minutes.
you could have one that's 1, 1, 1, 1.
1, 1, 1, 1.
And it corresponds to, it's just 3 ones. And it corresponds to 3. But if you had a span of them, you could add them together.
And get something in the span and get something in the space.
Yeah.
That is correct. But I think the problem with your argument is they're coming from two different eigenspaces.
Oh.
Well, when we talk about the eigenspace, we're not talking about all eigenvectors all at once. We're talking about like all the eigenvectors associated to lambda equals 0 is going to form a subspace. And all the eigenvectors corresponding to lambda equals 3 is going to form a subspace.
Oh, okay.
I'm not making any sort of claim about all the eigenvectors, doesn't matter what lambda they're from, are going to form a subspace. That's generally false, as this example would actually show.
Oh.
So let's go through a couple of examples where we find some corresponding eigenspaces and see what ends up happening. So let's go back to our good old C equals 1, 2, 4, 3. Hold on, I'm getting a phone call and I might need to take this. I'm not taking this. Sorry, lots of moving pieces to get through. We already found this thing had two eigenvalues. Lambda equals 5 and negative 1 were the eigenvalues. I'm not going to bother finding those again since we just did that. So what I want to do is I want to find the eigenspace associated to each of these eigenvalues, which will tell us what are the corresponding eigenvectors. John, which eigenvalue do you want to start with? What, 5 or negative 1?
Negative 1.
Start with negative 1? Okay. So if we want to take e sub negative 1, by definition, that's going to be the kernel of the matrix C minus negative 1 times the identity matrix. Or in other words, the kernel of C plus the identity matrix. You're here, I'm just using kind of this formula I circled over there. So how do we find the kernel of, or what is C plus the identity matrix going to be, Noel?
C plus the identity matrix would be 1, 2, 4, 4.
Close, not 1, 2, 4, 4.
No, 2, 2, 4, 4.
2, 2, 4, 4. Yeah. Exactly. So we take C, we add it to the identity matrix, we're going to get 2, 2, 4, 4 as our result. Oh, hey, we need to find the kernel of a 2 by 2 matrix. That smells like a standard 5 problem to me. Cameron, do you agree? So how do we find the kernel of a matrix? Remember, the kernel of this matrix is the set of all x, y that we can multiply this matrix by in order to get to the 0 vector. Kevin?
Is this where you find how many free variables there are?
We will need to do that at some point. I don't think we're quite ready for that yet. Because before we start looking for free variables, what do we need to do to our matrix when we're looking for the kernel?
Do we need to row reduce it?
Yeah, I don't think we necessarily need to, but I think the easiest way to find the kernel of your matrix is to start by row reducing it. because we said that kernel of a matrix is going to be the same if we row reduce our matrix. Image changes, but kernel will stay the same. So that was kind of our initial procedure.
I also can reduce if you I reduced it.
Well, aren't you special?
Yeah.
Okay. What do you get when you row reduce this matrix?
1 1 0 0.
So much what?
1.
Oh, you.
That's just me. I'm his mother.
Hey.
Professor's mother.
Coming early, I see.
Not much to do at your house.
1 1
You
0.
can see the sort of sass I have to put up with myself. Most of the sass that I've got from her. Okay, so Henry, what did you say you got for the reducer echelon form again? Sorry.
1 1 0 0.
1 1 0 0? Yeah, I think so. I think we can very quickly get there. We can just multiply top row by a half to get 1 1 4 4 and then subtract 4 times the first row from the bottom row to 0 out the bottom row. So, okay, so we need the kernel of the matrix 1 1 0 0. So now, Kevin, I think we need to get into what you were saying. We need to do something with free variables. So if we have that 1 1 0 0 times the vector xy comes out to the 0 vector, what does that imply about x and or y?
Well, if x equals minus y,
Yeah, so basically the equations we get from this is that x plus y is 0, and also, of course, that 0 equals 0. Ms. Gerstle, does 0 equal 0?
I believe so.
Does it matter what x and y are equal to, or does 0 always equal 0?
I'm assuming 0 always equals 0.
That this is true. Okay, so this turns out to be equivalent to just saying that x is equal to negative y. So how many free variables are we going to need?
One.
Yeah. So let's say we call y r. What would x be equal to then?
Negative R.
Yeah, negative r. So the kernel of that is going to be made up of all vectors that are of this form, which is all vectors that are scalar multiples of negative 1, 1. And what does that tell us? Well, that's going to tell us that the eigenspace E sub negative 1, which is the kernel of C minus negative identity matrix, is just going to be the span of the vector negative 1, 1. So Leah, to answer your question earlier, what do all the eigenvectors of this matrix look like that correspond to 2 lambda equals negative 1?
The scalar multiple of negative 1 1.
All scalar multiples of negative 1, 1?
Except 0.
Except the 0 vector. Yeah. So technically, this eigenspace will give you all the eigenvectors associated to negative 1, 2 lambda equals negative 1, but it also gives you the 0 vector, which is technically not an eigenvector. Yeah. So we can say from this that the eigenvectors of C associated to lambda equals negative 1 are all non-zero scalar multiples of the vector negative 1, 1 and R2. Yeah, John?
Can you explain the jump again from the jump to the free variable?
Sure. So basically, here we're asking the question, what does it mean for a vector in R2, xy to be in the kernel of this matrix? Which just means what needs to be true about xy in order for matrix times xy to come out to the 0 vector. So according to what Paul Joshua said earlier, this happens if and only if x is equal to negative y. So if we treat y as a free variable and say y can be anything we want, x just has to be the negative of that. And so basically what we found is that all vectors that can be written in the form that satisfy x equals negative y have to be scalar multiples of -1, 1 specifically.
What if we made x the free variable? Would it switch?
Then you would have something like r negative r, and you would get all scalar multiples of 1 negative 1.
Would that change the answer?
Not really, because the set of things that are scalar multiples of 1 negative 1 is the same as the set of all scalar multiples of -1 positive 1. Because just any negative scalar multiple of this will give you a positive scalar multiple of that, and vice versa. So, but basically you would get a different basis. You would get a different vector that spans the same set as this one. So it would lead to the same answer, but that would look slightly different. Does that make sense?
Yes. Thank you.
Cool. Any other questions or comments? How much time we got? I haven't got enough time. Let's do the same thing for lambda equals 5. So lambda equals 5. Hopefully you left enough room to write on that page. We need to find the eigenspace of the matrix C corresponding to 5, which is going to be, by definition, the kernel of C minus 5 times the identity matrix. Riley, what are we going to get if we take our matrix C and then subtract off 5 times the identity matrix?
And then you'll get -4, 2, 4, -2.
Or -2? Yeah, you subtract 5 on all the entries on the main diagonal, which will give you this matrix. All right, Henry, you row reduced this one already?
1, -1.
Well, hold on a second. Read.
I got 1, -1/2, 0, 0.
0, 0? Yeah. I think right away you can zero out the bottom row by just adding the first row to it. Get the bottom row is a row of zeros. And then the first row you can just multiply by -1/4 to get 1, -1/2 in that row. Okay, so in this case, what system of equations do we get from this one? If we want 1, -1/2, 0, 0 times the vector xy to give us 0, 0, what needs to happen here? When?
Yes, we have, let's see, it would be x minus 1/2 y equals 0.
And?
Oh, and 0 equals 0.
Can't forget the 0 equals 0. How can we pass up the opportunity to draw a pair of glasses on the board? Okay, so if x minus 1/2 y is 0, again, this kind of doesn't tell us anything. Cameron, what does that tell us about that x has to be equal to?
1/2 y.
Yep, so x has to be, let's try drawing this so y doesn't look like it's in the denominator. Would have to be equal to 1/2 times y. Alright, and if x has to be equal to 1/2 times y, John, I'll ask you again, how many free variables are we going to have this time?
1.
Corresponding to the variable?
X.
You could do it with you could do it corresponding to x. The way we've kind of been doing it in class is we let the stuff on the right side of the equations correspond to the free variables. But you could do it the left side as well. The way I would think about it is that xy has to be of the form r 1/2 times r, yar, which is going to be r times the column matrix 1/2 1, and then we can thus say that the eigenspace E sub 5 is going to be the span of just good old fashioned 1/2. So that the eigenvectors of our matrix C, which no longer exists on the board, but exist in all of our parts, the eigenspace associated to lambda equals 5 is going to be all scalar multiples of 1/2 1. Meaning the eigenvectors corresponding to lambda equals 5 are going to be all non-zero multiples, scalar multiples of 1/2 1. Alrighty, have a good Thanksgiving break, everybody. See you all in a week. So in a week from now, we'll go through the 1, 1, 1, 1, 1, 1, 1, 1, 1 matrix, finding its eigenvectors, where something interesting is going to happen. Slight spoiler. And that's going to lead us into some definitions of algebraic and geometric multiplicity as far as
But it's not.
hope you all have a good one, and adios.
Thank you.